Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Welcome to This Explainer. Today, we're diving into a topic that is just absolutely fascinating: complex analysis. We're going to uncover how incredibly strict, microscopic mathematical rules somehow give rise to the beautiful, global geometry of our entire physical world. It's kind of mind-blowing.
So, what exactly makes complex math so surprisingly elegant? Well, the secret is actually in how insanely rigid the rules become. When you move from standard real number calculus, where you're just moving back and forth along a 1D line, into the 2D complex plane, things change. You're navigating real and imaginary numbers simultaneously. The rules are so incredibly demanding here that they end up forcing the math into this beautiful, almost magical framework. We're going to build this up layer by layer. First, we'll hit the foundations of complex functions. Then, we'll look at integrals and harmonic fields, explore global limits and infinite series, jump into residue calculus and topology, and finally, wrap up with universe-bending conformal mapping. All right, part 1, foundations of complex functions. Let's get right into what it actually means for a function to operate on complex numbers. The absolute linchpin here is the concept of an analytic or holomorphic function. And wow, is it a spectacularly strict condition. You know how in standard math, a function can be differentiable once, but maybe not twice? Not here. In the complex world, if a function is complex differentiable in a neighborhood of a single point, boom, it's automatically differentiable infinitely many times. It can be perfectly represented by convergent power series. That is a massive superpower that sets the stage for literally everything else we're going to talk about.
To really grasp why it's so strict, you got to think about the geometry. In real math, you approach a point from the left or the right. Simple. But a complex limit, it has to be perfectly identical from absolutely any 2D angle of approach, a full 360 degrees. This forces the Cauchy-Riemann equations, where the partial derivatives of the real and imaginary parts must perfectly align. The function basically ignores the complex conjugate completely. It depends strictly on the complex variable itself. No exceptions.
But, sometimes this beautiful analyticity breaks down at certain points. We call these isolated singularities, and they fall into 3 very distinct buckets. First, removable singularities. This is where the limit actually exists and is finite, so it's well-behaved. Then you have a pole, where the function just shoots straight off to infinity. And finally, my favorite, the chaotic essential singularity. This is where the limit just doesn't exist at all, and the output dances wildly around the entire complex plane near that point. Total mathematical chaos. Okay, moving to part 2, integrals and harmonic fields. Let's zoom out from these individual points and see what happens with paths and physical fields. Remember those incredibly strict Cauchy-Riemann equations? Because of them, both the real and imaginary components of our analytic function act as harmonic functions. This means they both perfectly satisfy Laplace's equation. They act as harmonic conjugates. Basically, they are completely locked together. And this is exactly why this pure, abstract math matters in the real world. It perfectly models physical systems. Think about an ideal fluid flow. The real part of your complex function acts as the velocity potential, and the imaginary part perfectly represents the stream function, which is the actual path the fluid particles take. The lines of constant potential and the lines of fluid flow stay perfectly orthogonal, intersecting at exact right angles. And it does the exact same thing for electrostatic fields. It's like the math was custom built for physics. Now, if we draw paths and integrate through these fields, we get this deeply satisfying logical progression. First, Cauchy's integral theorem tells us that integrating along a closed loop in a simply connected domain gets you exactly 0 every time, which leads right to Cauchy's integral formula, proving that the values along a boundary completely and magically determine everything inside that boundary. And then Morera's theorem flips it in reverse. If your closed loops always equal 0, your function is definitely analytic. It's a flawless loop of logic. Let's zoom out even further for part 3, global limits and infinite series. We're going to see how these hyper-strict local rules impose massive, inescapable limits on the entire complex plane. This strictness has profound global consequences. Take Liouville theorem. It proves that any entire function, meaning it's analytic everywhere, that is also bounded just has to be a flat, boring constant. It can't go up or down without eventually flying off to infinity. And this cleverly guarantees the fundamental theorem of algebra, because if a polynomial had no roots, its inverse would be a bounded entire function, which we just established is impossible. So, every non-constant polynomial has to have at least one complex root. Checkmate. Then we have the maximum modulus principle. This rule is wild. It tells us a non-constant complex function can never, ever peak on the inside of a given domain. Never. Its absolute maximum value is always pushed entirely out to the boundaries. The interior values are always just an average of the boundary values, making local interior peaks mathematically impossible. To handle these functions locally, we represent them as infinite series. Taylor series work perfectly for those pristine open disks where the function is completely analytic. But what if your space has a hole in it, like a donut-shaped annulus wrapping around one of those isolated singularities we classified earlier? Well, then we have to break out the Lorentz series, which brings in negative powers to account for that pesky singularity right in the middle. So, part 4, residue calculus and topology. What's our practical tool for actually navigating integrals around those tricky singularities? We extract something called a residue. When you look at that Lorentz series expansion around an isolated singularity, the residue is just the specific coefficient of the inverse term, the term to the power of -1. It might seem like just a single random number, but it is basically magic. It captures the fundamental topological behavior of the entire singularity. Now, Cauchy's residue theorem synthesizes all these core concepts together into one elegant tool. It lets us solve total nightmare integrals just by finding the isolated singularities, grabbing their individual residues, summing them up, and multiplying by 2πi. It literally turns incredibly complex, headache-inducing calculus into basic addition. It's a real game changer. And we can even use these winding paths for topological counting. With the argument principle and Rouché's theorem, we can count the exact number of zeros and poles hidden inside a region just by watching how the function behaves on the boundary contour. Engineers actually rely on this daily. They use it to verify the stability of dynamic systems like airplane control systems without ever having to track down the exact roots. Finally, part 5, conformal mapping and geometry. For our last conceptual leap, we're looking at how these functions visually warp space itself in geometric function theory. Because of their insanely strict internal logic, analytic functions with a non-zero derivative act as conformal mappings. What does that mean? Well, they might massively twist, scale, and stretch a grid on a global level, but at the micro level, they perfectly preserve every single intersecting angle and orientation. So a 90-degree intersection before the mapping, it remains exactly a 90-degree intersection after. Which leads us to the astonishing Riemann mapping theorem. It proves that almost any open, simply connected shape, no matter how wildly deformed or weird it is, can be perfectly, conformally morphed into a simple, standard unit disk. Taking it even further, the Schwarz-Christoffel transformation gives us the exact integral formula to unfold a simple upper half plane into any sharp, straight-edged polygon. Just incredible stuff. This essentially builds a practical dictionary of geometry. We use these exact formulas to morph complex physical domains. Say you've got a tough fluid flow or heat transfer problem in a weirdly shaped space. You can use an exponential function to map an infinite horizontal strip perfectly into an upper half plane. You map your tricky physical shape into a simple disk or half plane, easily solve the math there, and just map it right back. It's an absolute superpower. Ultimately, this explainer on complex analysis is a story of profound unity. It flawlessly connects pure analytical differentiability with global topological geometry. Those microscopic rules of differentiability we started with,
They seamlessly construct the vast geometric reality of physical fields, forces, and fluid flows. It is just a massive, logically airtight framework. Which leaves us with a truly profound question to ponder as we wrap up. If such rigid, elegant mathematical rules can so perfectly model and dictate the global shape of our physical world, what other hidden, elegant structures are secretly governing the universe around us, just waiting to be discovered? Thank you so much for exploring this with me today.
Like what you shared.
This website makes learning so easy. I found all my resources here.
Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious mind.